Sarah, what's up? We're back this time from Singapore, doing our world tour still, and we're over here, so wanted to give you a little bit of a heads up on bonding. Okay, that's the next topic. Today is Sunday, the 12th, I believe, of November, and you guys in your chemistry class had a quiz this past Friday, the 10th of November. So I wanted you to be as comfortable as you possibly can with bonding, because it can get kind of nutty. Now, what bonding is, it just means, hey, how do compounds, which are, like sodium with chlorine to make sodium chloride, which is table salt, what makes them stick together? How they just like say, oh, here's a sodium, here's a chlorine, we're going to match up. Like, why does that happen? Okay, for example, that's one kind of bonding. Or you see a coin in your pocket or on the table or something like that, a coin. All those metal atoms are bonded together. They're stuck together. They stick. Why do they do that? Okay? Or even gases that we breathe. Like, why does hydrogen, any diatomic gas, why does it stick together? Why? How do bonds even work? Okay? Those are the things that keep these atoms together to form molecules. They are bonds. What kinds are there? How do they work? So that's what we'll be discussing in this video. Then in the next video, we'll get into like the whole kind of logic of the kinds of questions that they could ask you, not just the conceptual stuff, but when you actually have to write stuff out, kind of math-wise, but not really math. Okay? So there are different kinds of bonds, and the three kinds that your teacher highlights first is ionic. There's also metallic bonds, and there's also covalent bonds. Now, those are not the only three kinds of bonds. So don't think that you're getting off easy only learning three, but these are the main three. These are the three that we're going to start off with. Okay? So, in ionic bonds, here are the three, by the way, just so you can see them. I still got my whiteboard right here. Ionic bonds. Ions are bonded with ionic bonds. Okay? What is an ion? Charged particle. Okay? So, usually, metal and non-metal. The one exception is hydrogen, which is not a metal, yet it lives on the far left in the periodic table, so it's with all those metals beneath it. So, ions, remember, they gain or they lose electrons. Stuff on the left of the periodic table loses electrons. Stuff on the right of the periodic table gains electrons. Either way, there's what's called a charge imbalance, okay? You got something that has lost electrons mixing up with something that has gained electrons. Okay? So, I'm going to write down is transfer of electrons. That's what causes ionic bonds. Some metal, something on the left of the periodic table, gives, full-on gives, donates its electron to something on the right, a non-metal. Okay? To make it, then this goes back to like the electron, the valence electrons. How many valence electrons does something on the left have? Usually either one or two only. So it wants to get rid of those one or two valence electrons rather than take on five or six or seven more to make its outermost energy level of electrons full. So you usually, except for hydrogen, have a metal giving one or two electrons away to a non-metal to form an ionic bond. Also, that whole structure with a metal and non-metal is called an ionic compound, and the two atoms in the ionic compound, or more atoms, but the simplest case is two atoms, those are bonded with ionic bonds. Okay? The cation, which is the positively charged ion, literally just gives one or two electrons to the anion. Okay? Electron donation. So now, both, or if there's more than two, all three, all four atoms in the ionic compound are happy. Their valence electron shell, their outermost energy level is completely full with 8 electrons. For the most part, 8 electrons. Hydrogen, again, only has 2. So hydrogen is going to be a big exception here. But that's what happens. Okay? And why that's so powerful is because in chemistry, much like in life, opposites attract. Okay? So a cation is the positively charged guy. The anion is a negatively charged ion. Positive and negative are opposite signs, they're opposite charges, and they therefore attract each other really, really, really well. So the strength of an ionic bond is the strongest, okay, of them all. There are going to be some kinds you learn, like there's hydrogen bonds that are coming, which are actually, in my opinion, okay, they're really stronger, but those are between molecules. They're not inside of molecules. So they're a little bit different classification, okay? Hydrogen bonds, though, keep this in mind, mental note, hydrogen bonds are extremely, extremely strong. We'll talk about those in future videos. But for right now, we're just talking intramolecular, between atoms and an electron, not intermolecular, between physical molecules themselves. So we're not mentioning hydrogen bonds yet, just talking straight up ionic, okay? Next up, metallic bonds. I just erased covalent. Hold on a second. Okay, metallic bonds. Those are next. And those are not quite as strong as ionic bonds because they don't involve charge really. They're just, hey, a lot of the transition metals. You know, you got the first 4 rows, and then that 4th row, you got that big block in the middle now. You got the first 3 rows where there's that big space in the middle of the periodic table. Then beneath that, the 4th row, going across, you start hitting all these crazy transition elements. That is where a lot of metallic bonding comes in. Okay? They're bonds between atoms of metals. There are bonds between atoms of metals, and that's really it. They're not quite as strong as ionic bonds because they have no ionic charge to them. There's no attraction. There's no positive negative aspect to them. Just connected, connected, connected. Okay? Because of that, the metals that you may have wrapped up pizza or something like that. Hey, put it in the fridge, wrap up the pizza, and you wrap it in either tin foil or aluminum foil. Both of those, by the way, are transition metals. You can bend those pretty easily. Okay? You can manipulate the way they look because they're not as bonded as strongly together as ions are. Table salt, by the way, is a very, very common, NaCl, a very common ionic salt, all right? And it uses ionic bonds. And if you ever look at it, if you have a salt shaker and you look at them, they're pretty much like cubes, perfect cubes. We'll talk about that too. And there's a reason for that. Okay? So metallic bonds are just bonds between metals, and they use what's called a sea of electrons. They don't really use them, but there's this consequence of metallic bonds. Okay? Share the electrons for covalent. I'm just writing that down for later. So, if you remember from last time, we talked about periodic trends and electron shielding, and like the bigger an atom is, or the more electrons it has, the further away an electron is from the nucleus, the less attraction it has to that positively charged nucleus. In the same way, it's just like gravity. The further two planets are from each other, like a planet is from our sun, anything like that, its gravitational pull, the force of gravity between them, is going to be less and less because it's an inverse square relationship. So what that means is if your distance doubles, the distance between two bodies doubles, either in electric charge or in gravity, the force between them gets cut by 1 over 2 squared, because doubling is 2. You square that, make it a fraction, that's what happens to the force. Okay? So it happens here as well. And the further your electrons get from the positively charged nucleus, the less, by squaring and inverting, that force of attraction goes down. So these faraway electrons in metals, they are not really that drawn to the nucleus. So what happens is these electrons on the far outside realms of an atom, they kind of like stray away. They're kind of attracted, but not really. So what happens is they move, and in atoms next to the atom I'm talking about, those far electrons move. And so you got all these moving electrons because they're not really that attracted to each other. Okay, no, I shouldn't say each other. They're not really attracted to their home nucleus, let's say. Okay, but they repel each other. So what happens is you got a lot of movement on the surface of a metal from those electrons that are not really that attracted to their home nucleus, yet they're repelling each other because they're all negatively charged. And remember, opposites attract, but negatives repel. So what happens is you get this sea of electrons. It looks like an ocean just flowing back and forth, back and forth, back and forth. And from physics, I believe you remember, or if, man, I'm trying to remember if you covered electricity. If you did not, whenever there is a charge flow, like whenever charges, move, okay, whenever electrons move at all, you have what's called a current, and currents produce electricity. That is why metals are very, very good conductors of electricity, and you don't want to be out in a thunderstorm with a metal umbrella saying, oh, I want to stay dry, because it's going to attract, electric current's going to, lightning could hit your umbrella, and then you look like Wile E. Coyote in the cartoon. So you don't want that. Now, property of metals then. Very, very good conductors of electricity, metals are. Ions, just like in solid form, there's no movement of charge. Once the electron is donated from the positive metal to the negative non-metal, it's locked in. There's no more charge movement. So a solid ionic compound, like table salt, just chilling on your table, you want to put it on some meat or something, okay, cool. It's not going to really conduct electricity that much because the charges themselves are not moving. But once you dissolve something, like if you put salt into water, by the way, then what happens is dissociation. That's a very, very key word. Dissociation right there, okay? It's like association, but it's the opposite of association. If you associate with somebody, you're there right next to them, okay? If you dissociate from somebody, you pull away from them. So what happens is when you put salt into water, the water, through various chemical properties of attraction and all that stuff, it breaks the ion apart back into like sodium and chlorine. It'll take that table salt, for example, and pull the sodium ion away from the chlorine ion, and then you have moving in the solution, in the water, you got positively charged particles moving around, the sodium, and you got negatively charged particles moving around, the chlorine. And whenever you have a flow of charge, any movement of charge at all, you got electricity potential, okay, for conduction. So we say that metals are very, very good conductors of electricity, and dissolved ionic solids are very, very good conductors of electricity. Solid ionic compounds are not. And there's another vocab word I want you to know. It's called aqueous. Usually in chemistry, it's abbreviated by just AQ. Aqueous means a dissolved solid. That's all it means. It doesn't mean it itself is a liquid. It means it's been dissolved in a liquid. So it's created a solution of some kind. Okay? So what we say is solid ionic compounds do not conduct electricity at all. They're real crappy at it. But aqueous ionic compounds, those are good for conducting electricity. Okay? So I know this video isn't as much mathy and like doing problems as because it's a lot of theory that goes on with this. So rather than you just reading your notes, I want to kind of speak on the stuff a little bit so it's a good companion for you. Okay? So I'm trying to make this entertaining, but there is a lot of info I just want you to be comfortable with. So you could rewatch this, not that you'd want to because this is probably boring enough, but I want you to get this down. So you feel free to watch it. You don't have to listen to everything and get everything the first pass. That's why I'm going to make this a little bit short, hopefully. But you know me, I like to give you more than you expect, so maybe it's going to run a little bit long. I hope not, but it might. So next, covalent bonds. Those are the weakest of this set of three bonds. So strong, kind of weak, okay? Now, covalent bonds. It's not a metal and a non-metal anymore. Ionic bonds join a metal with a non-metal. Covalent are between two nonmetals. Covalent bonds have two nonmetals, so maybe nitrogen and oxygen, or carbon and oxygen, fluorine gas. Okay, all those kind of gases, or bromine if it's liquid. If it's a liquid. All these covalent bonds between those atoms, they're from electron sharing. Okay. You can think of ionic bonds as happening where, hey, I'm a cation, I'm sodium, you are chlorine, you're an anion, I'm just going to give you one of my electrons, and I don't want it anymore because I'm going to be happier without it, and you're going to be happier with it, so we both win. Covalent, it's more of like, you know what? We're going to share electrons so that we're happy. Okay? So, let's say there's carbon and there's oxygen, both nonmetals, by the way. Let's say one or two or more of electrons are going to be shared. They're not going to just orbit carbon. They're not just going to orbit oxygen. What they're going to do is they're going to, in a sense, not really, but you can imagine it this way, they're going to form like a lazy 8 around both. They're going to go around, they're going to orbit both nuclei. Okay, they're going to orbit around the carbon and the oxygen. That's shared. It's not as powerful as just flat out donating, because we're not saying one side is now positive, one side is now negative. Okay, what we're saying now is that yes, there's going to be some flow of, but it's going to be more like a shared connection. Okay, because of that, and because there's not so much positive versus negative, but it's like negatives just moving around everywhere. Yeah, there's going to be some electricity, but it's not going to be as strong. Okay, so the bond, the covalent, when atoms bond covalently, let's say, it's not as strong an attraction as these two guys. Okay, so that's just getting these down. Okay, the 3 kinds of bonds. Now, I'm going to pause right there, just so you can digest that, and then in future videos, I'm going to get into some more topics about, you know, melting point of these, boiling point of these, what makes some ionic compounds have higher melting points than others, and all that stuff, because these are just properties of these compounds. Okay, what I want to make sure you know though is what an ionic compound is: a metal and a non-metal, or you know, you could have maybe calcium fluoride, which is CaF2, so you have 3 total atoms, not just 2 of them. So a minimum of 2, and metals with non-metals. Okay, metallic bonds, those are just metals together. Okay, and then covalent bonds, 2 non-metals together. So those are the main differences. Go ahead and just rewatch this video if you want, just to get comfortable with all the little stuff I was talking about. In a future video, I'm going to talk more and more in depth, and we're going to get into Lewis dot structures as well. You don't know what those are yet, unless you've read ahead, but they're not bad, although they can seem bad. But I'm going to give you a good technique, like a series of 3 or 4 steps, just to take you all the way through how to do those and make sure that you're good with those. All right? So until next time, which maybe even today, I don't know, but I'm going to upload this, give you some more.